Bonjour, good afternoon, everyone. My name is Rainer Kling. I'm with Alphanov. I'm the business unit manager of laser processes, Alphanov in Bordeaux, and it is my pleasure to guide you through this afternoon session. We have a quite international representation of talks, and each talk is designed for 30 minutes. 25 minutes presentation and 5 minutes question. And we will start this session today with Maxime Chambonneau, who is with Jena University right now. And he will present us his work on filamentation of bulk silicon with ultrashort pulse lasers. So, Maxime, if you're ready, the floor is yours. Normally, you should start in 1 minute precisely, but I guess everyone is connected right now and you may introduce yourself.
Yeah, okay. Can you see my slides and screen?
Yes, perfectly.
Great. Thank you, Rainer, for this very kind introduction, and good afternoon, everyone. First of all, I would like to thank the organization committee, especially John Lopez and Fanny Voinson, for giving me the opportunity to present this work. It's my great honor to start this closing plenary session, actually. So, as introduced before, my name is Maxime Chambonneau, working at the Institute of Applied Physics in Jena, Germany. And today I'm going to show you how understanding filamentation inside silicon can be crucial for devising new applications inside this material. So here is the outline I will follow. It's pretty straightforward. First, I will introduce the context concerning ultrafast laser silicon interaction, and then I will present different applications we have found at our institute, including optical functionalization of silicon with picosecond pulses, semiconductor to metal ultrafast laser welding, and also ultrafast laser dicing of silicon. So first, the context. Well, that will be a secret for no one here in this conference, that ultrafast lasers represent an extraordinary tool for functionalizing materials, especially dielectrics, which are transparent materials. And the reason is shown here on the left. It originates from the fact that at those ultra-short timescales, it is possible to separate the causes, which is the absorption of photons, from the consequences, which is the material response. And this allows functionalizing transparent materials for different kind of applications listed here, for instance, fiber optics, additive manufacturing, microfluidics, data storage, and so on. So the question is now, is it possible to transfer the knowledge concerning laser writing to the bulk of silicon, right? On principle, this looks quite simple and straightforward. However, if one tries to do laser writing in bulk silicon, they will face two major problems. The first one consists of technological difficulties. As you can see here, silicon is not transparent to visible light, so there is a need for ultrafast infrared laser sources. And of course, we also need some optics and detectors, which are usually more costly and less efficient in the IR than in the visible. But if this was only about technological difficulties and technical problems, that still could be possible to achieve laser writing in bulk silicon. Now, the main problem is originating from physical limitations. Specifically, when you look at the nonlinear refractive index of silicon, it is about 100 times higher than the one of fused silica, for instance, meaning that at relatively modest peak power or input pulse energy, there will be a competition between carry effect on the one hand, which focuses the beam, and plasma defocusing on the other hand. In other words, we are in the filament regime, which is a highly nonlinear propagation regime. And this has two major consequences. First, as shown here, there is a nonlinear focal shift upstream the laser when you increase the input pulse energy. And the second consequence is illustrated here. There is a saturation of the intensity inside the bulk of silicon. And when you take those two consequences together, you can conclude that there will be some strong delocalization of the energy deposition in the prefocal region. Also, related to this, one can conclude that increasing the laser energy is usually a bad strategy for hoping to modify silicon. So why should we still try to push these limitations? Well, as you know, silicon is because of its electrical properties. Silicon is the backbone of constantly growing markets, including quantum technologies, ultrafast microelectronics, photovoltaics, and so on. To date, the best way to fabricate a silicon-based device is to use lithography methods such as silicon on insulator, SOI. However, they show some important drawbacks, especially it's limited to a 2D configuration. It requires a clean environment. It's time-consuming and thus costly. On the opposite, laser inscription would be potentially nice for a 3D flexible, fast, and contactless way to functionalize the material. To date, nanosecond laser pulses can be used for modifying silicon, but the degree of control is kind of limited as the interaction is thermally driven in this long pulse duration regime. So I will move to my first application we found concerning waveguide writing. And we basically wanted to answer the following questions. Is it possible to write low-loss waveguides inside silicon with picosecond laser pulses? Then if yes, what is the estimated refractive index change? And finally, what would be the origin of the waveguiding? Well, to answer all those questions, we have developed the following setup depicted here. It works at 1.55 micron wavelength with 800 femtosecond pulses. Then we adjust the input pulse energy as well as the beam size optically before the beam is focused to the silicon target by an objective lens. Besides, we have two microscopes working both in transmission, which allow us to basically monitor the interaction in a three-dimensional way. So what is the trick we have found for modifying bulk silicon? Well, we work here with an exit surface which is grinded, like a very bad polishing. And then by focusing the beam at the exit surface, we can create some kind of crater, and then we move the focus upstream the laser towards the bulk of the material. And by doing so, we could inscribe some lines, and we checked the waveguiding properties with this simple setup here, relying on continuous light injection inside the waveguides with two different microscopes, one allowing to image the near field intensity profile, and the second one allowing us to monitor the scattering. With this setup, we have found that our waveguides show a coupling efficiency of 53% and a transmitted power around 25%, which is consistent with the scattering images. So to conclude on this, we have found some damping losses around 4.5 dB per millimeter, which is the lowest for laser written waveguides inside silicon to date. Also, we have demonstrated in our group that it was possible to inscribe with the same technique a 50-50 Y splitter, or also called multiplexer. As you can see here, this is on the top the input, and on the right the output, which is basically an additional proof of light guiding, and it shows similar damping losses. Okay, so what is the refractive index change associated with the waveguides we have written? Well, to answer this, we rely on two different methodologies. The first one is known from the 90s, relying on an inverse Helmholtz equation, as you can see here. And a second method we have developed relies on the overlap integral for the waveguides, as well as a beam propagation model. And then we could compare basically the experiments to some simulations by shifting transversely the waveguide with respect to the input continuous beam. Both of these methods conclude on some refractive index change on the order of 10 to the minus 3, which is in very good agreement with highly confined modes. Then, what is the origin of the waveguiding? Well, to answer this, we have carried out other measurements. First, with transmission electron microscopy, where here you can see some nano defects along the waveguide track. Then, with electron diffraction on unmodified and modified silicon, we have seen no difference in terms of crystallinity, so we concluded that the crystal structure was maintained. And more recently, we have carried out some annealing experiments at different temperatures, where we have seen that both the mode field diameter increases and the delta n, so the refractive index change, decreases with the temperature. So our conclusion is that the waveguides we have written rely on strain induced by dislocations. So here is the take-home message for this application. We have performed some exit surface seeded inscription with picosecond laser pulses. With this technique, it was possible to inscribe low loss and single mode waveguides and Y splitters with a refractive index change higher than 10 to the minus 3. And the waveguides rely on strain induced by dislocations in the monocrystalline material. Then I will speak about our second application, which is semiconductor to metal ultrafast laser welding. Well, there were a lot of presentations on this topic, so I guess you are all familiar with this technique. So basically, laser welding is a very nice alternative to traditional methods because it consists of energy deposition at the interface between two materials, and thus provides a fast, clean, and contactless way to join them. Well, it was shown to be applicable in many material configurations, such as glass to glass, glass to semiconductor, glass to metal, polymer to polymer, also more recently, ceramic to ceramic. However, in the semiconductor to metal configuration, there is nothing too convincing so far. So let us have a try. To do so, we will employ essentially the same setup, except that we work around 10 picosecond pulse duration now. And we illustrate semiconductor to metal ultrafast laser welding with silicon and copper. We have a macroscope for positioning for knowing the relative position of the focus with respect to the entrance surface of the silicon sample. And after welding with those conditions, we have evaluated the bonding quality post-mortem by separating the two samples with an indenter. Okay, so let's try. If we set the energy to 300 nanojoules, then one can measure a shear joining strength of 30 kilopascal. Okay, and then what if we double the energy? Well, then the shear joining strength is 10 kilopascal, which is a surprising behavior, right? Like by increasing the energy, you would expect to have a better welding. But the main question here is that sufficient? And sadly, the answer is no, as the samples in this case are easily separable by hands, and moreover, the typical values for other material configurations or traditional bonding methods are on the order of 1 to 20 megapascal. So why? Well, I gave partly the answer in the beginning of my talk. Everything originates from the filamentation during the, the propagation through silicon, leading to both an intensity clamping and a nonlinear focal shift. So here are the two solutions we propose. For the intensity clamping, we propose an interface with a metal in the frame of semiconductor to metal laser welding, meaning that the absorption is increased, which is actually what we aim for. And second, for solving the nonlinear focal shift, we propose a filament relocation at the interface between the two materials, meaning that the intensity should be increased. But to do so, we need for nonlinear propagation imaging. And basically, this is actually what we did with this setup shown here. We imaged the nonlinear propagation inside silicon. Here you can see it's nothing else than an inverted microscope working in transmission, which allows us to retrieve the 3D fluence distributions, as you can see here on the right, as well as the nonlinear focal shift delta Z as a function of the input pulse energy. On this data here on the right, one can distinguish three distinct regimes. First, for extremely low input pulse energy, we are in the linear propagation regime as confirmed by simulations, which are point spread function analyses. Noteworthy, this tool is open access and open source developed by my colleagues. So if you want either to have more details or, well, try to have fun with it, just feel free to check those two references here. Then going back to the data here on the right, for intermediate input pulse energies up to 100 nanojoules, we can clearly see that the focus is unambiguously shifted upstream the laser. However, the overall shape is conserved. And then when we move to more energy, like more than 300 nanojoules, we are clearly in the filamentation regime, as for instance illustrated here with these focusing and defocusing dynamics. So the conclusion of this data is that increasing the input pulse energy leads to an energy deposition far from the interface, in very good agreement with a semi-analytical model that we have developed. Okay, let's try to push a little bit the limits. Here on the left, you can see the shear joining strength for two different input pulse energies without in red and with in green delta Z precompensation. The striking feature here on the left is that precompensating the nonlinear focal shift delta Z leads to a much better welding. Okay, so what now if we keep this delta Z precompensation strategy, but at the same time increase the input pulse energy? Well, the results are essentially shown here in blue, where you can see that it is possible to reach around 2 megapascal for input pulse energies near 1 microjoule. And this is suitable for applications, so as illustrated here on the left. The reason for this success is that precompensating the nonlinear focal shift leads to an enhancement of the maximum fluence as well as the energy reaching the interface. Noteworthy, as illustrated here by this purple line, there is no welding possible for input pulse energies below 100 nanojoules, meaning that silicon to copper ultrafast laser welding is solely achievable in the filamentation regime, meaning that it's really important to measure and precompensate the nonlinear focal shift in the end. So here is the take-home message for that part. We have achieved the first semiconductor to metal ultrafast laser welding by characterizing picosecond laser-induced filaments inside silicon. And we have measured megapascal shear joining strength that are compatible with applications. If you want to know more about the whole process, please feel free to scan this QR code here, which will lead you to our latest publication on this topic, which was published recently in Laser and Photonics Reviews. Great. So I will now move to my last, the last part of my presentation, which is entitled "Laying the Foundations of Ultrafast Laser Dicing." Well, the motivation is, again, we wanted to answer the following questions, like, is there really no way to modify silicon with femtosecond laser pulses? Second, is ultrafast laser transverse inscription possible? And finally, is it possible to induce some weakening effects in some silicon wafers for dicing them into individual chips, as illustrated here? I guess you are all familiar with this kind of sketch. Well, to answer all these questions, we rely on the following experimental arrangement, which is essentially the same as previously, except that now the input wavelength is around 2 microns, which is kind of a spectral optimization, because then the deposited energy inside the material is the highest. We also work with 750 femtosecond pulses, but with distorted temporal profiles, as you can see with this AC trace here, which is kind of a temporal optimization. As in the literature, it was recently reported that non-perfect Gaussian pulses are beneficial for achieving modifications inside the bulk of silicon. And a third optimization is illustrated here, which is a spatial optimization, which consists of counterbalancing the spherical aberrations which are provoked by the A-sphere reported here, with like counterbalancing them with the spherical aberrations which are induced by the interface between air and silicon. And by performing some linear propagation simulations, like very simple, we could see that around 100 microns or 120 microns, the intensity is theoretically enhanced in that case. So what now about the reality of experiments? Well, to answer this, we have carried out some damage probability measurements at different focusing depths and input pulse energies. And what we have seen is that it was possible to produce some repeatable damage inside silicon, like with 100% damage probability, in a very narrow focusing depth window around 100 or 120 micrometers. And this window behavior was consistent with nonlinear propagation simulations, as shown here in the middle, where you can see that the peak intensity as well as the peak delivered energy is higher when the focusing depth is around 100 micrometer. Concerning the modifications, well, they consist of micro bubbles aligned along the optical axis with a positive refractive index change as measured by infrared interferometry. Okay, so this was for single pulse and single site. What now if we move the sample perpendicularly to the input laser beam? Well, in this case, we have seen that it was possible basically to inscribe some continuous or discrete lines, but in the bulk of the material. And the line morphology was discrete, steady, or erratic. So discrete here for high speeds, steady for intermediate speeds, and erratic for low speeds. And we have also carried out additional measurements at different input pulse energies, as you can see here on the right. And basically what we concluded is that we need absolutely a modification probability of 100% in order to be able to reach the continuous transverse line writing regime, which is here in red and in green. This means that intrinsic breakdown is the origin of the the transverse line writing. And besides, we have carried out some three-point breaking tests, as illustrated here, and we have seen that the lines act as weak points inside the material, meaning that the breakage is basically guided when a force is applied. In contrast, when the wafer is not modified and you try to do this kind of three-point bending test, then the wafer is destroyed in 1,000 pieces. So here is the take-home message for this last part. With a triple optimization in spatial, temporal, and spectral domain, it is possible to produce repeatable single-pass modifications. We have achieved the first transversely written lines inside silicon with femtosecond laser pulses. And these lines can be used for wafer dicing applications. So to summarize, in-volume laser direct writing is usually limited by filamentation, which prevents the production of permanent modifications. But you can bypass these limitations by using exit surface seeded inscription for low-loss waveguide writing as well as multiplexers. By taming filamentation inside silicon, it offers a new avenue for welding semiconductors to metals. And with a space-time spectrum optimization, it is possible to unlock ultrafast laser dicing. I would like to thank all my colleagues from my group, the group of Stefan Nolte in my institute, also the group of Jens Limpert, same institute, my colleagues from different academic institutions all around the world, and some industrial companies that help a lot for this work. And finally, this is my last slide. If you need for more information, please feel free to scan here this QR code, which will lead you to all our publications on this topic. Or alternatively, you can contact me anytime at the following email address here, especially if you are looking for patents to license on these applications: optical functionalization, welding, and dicing. So I would like to finish by thanking you for your attention.
Thank you very much, Maxime, for this very interesting topic and a very clear presentation.
Thank you.
The floor is open for questions. So I could not find other questions than mine, but I have, in fact, plenty. So we will easily cover the 5-minute time. I start with the first one on your filamentation results, and you wrote in your title that you try to address monocrystalline but also polycrystalline silicon. What do you expect passing on polycrystalline silicon? Will you have wavefront distortions on grain boundaries, or do you expect to have the same filamentation results?
Well, that's a good question. Actually, nobody in the past studied the influence of the polycrystalline features of silicon on the filamentation. Well, I would expect, as you mentioned, that there could be some wavefront distortions on the grain boundaries, depending on the size of the grains compared to the wavelength, of course.
So for solar cells, the dicing is even more challenging than what you showed on the monocrystalline, right?
I would say so, but without any experimental evidence. But this is something that should be tried in the near future.
And do you have any proof that you're weakening, in fact, the crystalline structure? Did you make breaking tests already, or is that foreseen in the future?
No. We did some breaking tests, and yeah, the breaking was much easier and guided when the transverse lines were written inside the material.
Okay, very nice. Another question that I did not write down, but I would like to ask you orally is, if I recall your introduction correctly, you made all the trials with a 1.5 micron laser. What do you expect if you go to other wavelengths? We know silicon is like a window in a large area in the mid-infrared. So the intensity clamping has been extensively studied in the near infrared, close to 1 micron. If you go to longer wavelengths, what do you expect?
Well, we mainly investigated not only 1.55 micron wavelength, but also around 2 microns with those thulium-doped lasers. But this is still in the 2-photon absorption regime. Well, if you look at some simulations, well, the intensity clamping and all these filamentation effects will occur whatever the wavelength, but possibly this is actually a very good question, because we do not know if higher wavelength would be beneficial or detrimental for breaking, well, for modifying silicon.
Okay, and then we have a question from John. Can you dice along curved trajectories?
We did not try. Theoretically, if you can produce some voids in the bulk of the material, I would say yes, it is possible to dice along curved trajectories. Again, this is typically possible with nanosecond pulses so far, except that the breakage is not too clean because of those thermal effects during the interaction. But theoretically, there is no real limitation to this.
Okay. And then we have another question from John. Have you tried SSTF in order to avoid nonlinear detrimental effects in silicon?
Okay, so SSTF for the audience is simultaneous spatio-temporal focusing, right? Well, we did not try actually, but yeah, this is kind of a complicated setup, because you need a spatial chirp, like separate the wavelength before focusing, and then they recombine in the material at a single point. But yeah, typically this could be tried in the near future.
All right. I think we are perfectly in the timing. If there are no further questions, we all thank Maxime again for his nice presentation.
Thank you.
And